Hello students, in the last class we have seen the definitions. Now we are going to see some of the important theorems with proofs from that unit 3. Okay, these are very important questions. Now see here, prove that a ring R has no zero divisors if and only if cancellation laws hold in it. See, remember students, just to prove today's theorems we need just definitions. With the definitions only we are going to prove all the 3-4 theorems what I am saying now. Okay, right, here what they are saying, no zero divisors. What we are going to prove, if and only if condition, cancellation laws hold in it. Okay, so no zero divisors means yesterday we have seen the definition of zero divisors. Okay, so what is zero divisor definition? Whenever our a not equals to 0 and b not equals to 0, their product a dot b is equals to 0, this is a zero divisors definition. Okay, right, if any of the property means either a is equals to 0, b is equals to 0 satisfied, no, then we will say that it has no zero divisors. It has no zero divisors if any of them, either a or b, is equals to 0. Okay, so now to prove, so first we will prove in we will take R has no zero divisors and we will prove cancellation loss holds. Then conversely we will take cancellation loss holds and we will prove R has no zero divisors. Okay, right, first of all R has no zero divisors I have assumed. Okay, so R has no zero divisors means we have to write down the zero divisors definition in converse part, means it is not zero divisor, means it is not satisfying that condition, we must write down. Okay, here I am taking a comma b comma c belongs to R such that our a not equals to 0, ab is equals to AC. Okay, remember here our a is not equals to 0. If I take the condition AB is equals to AC, if I send here AB minus AC is equals to 0, if I take A common, B minus C is equals to 0, B minus C is equals to 0. Since here we are taking A is not equals to 0, no, because it has no zero divisors, at least one of the element not equals to 0, not equals to 0, if I take B minus C should be equals to 0 compulsory. Okay, therefore B is equals to C. If R has no zero divisors, then the cancellation laws hold in R. Okay, then the cancellation laws hold in R means cancellation law means it is a left cancellation law actually. A get cancels and B is equals to C. This means the cancellation law. Okay, right, now conversely we will assume that left cancellation law hold in R. Okay, because we have cancelled left elements, no, so here we will see left cancellation law holds in R. Now if a comma b belongs to R such that ab is equals to 0 for a not equals to 0, b not equals to 0. Okay, so if a into b is equals to a into 0, a into 0 is equals to 0. So what happens, my a into 0 is nothing but 0 from the left cancellation laws of elements. This is a contradiction. Okay, now this is a contradiction because if it has 0 divisors it should not equals to 0, but here we got b is equals to 0, which is a contradiction. Okay, so means our zero divisors definition is not true, so therefore R has no zero divisors. Clear? Right, next theorem, prove that, very important theorem students. See here, prove that every field is an integral domain. Give an example to show that converse need not be true. Okay, right, here they asked only in one question that field is an integral domain. We have to take the field definition and we need to prove the integral domain. Yesterday in the last class I have said that field means non-zero element which has multiplicative inverse, and integral domain means it does not have no zero divisors. Okay, at least any two elements, it has no zero divisors, then it is an integral domain. Now here first of all we will assume field, then we will prove that is an integral domain. Let, what is the proof? Let f be any element you can assume it is a field. Okay, so compulsory if it is a field, it is a commutative ring with unity. First of all, whenever it is a field integral domain, you have to remember that those are commutative ring with unity. What actually we are going to prove? To prove F is an integral domain if it has no zero divisors. We have to prove actually F is an integral domain. That means what we are proving it has no zero divisors. It has no zero divisors means, so here first of all F is a field they are saying. Okay, when it is an field, a non-zero element, it exists inverse. Okay, always you remember, field means a non-zero element which exists inverse. See here, A is not equals to 0. Okay, so A not equals to 0 and AB is equals to 0, compulsory A inverse exists because it is a field. Our A comma B belongs to field elements, right? Since A belongs to F, there exists A inverse belongs to F such that A inverse A dot B is equals to A inverse. Here already we have AB is equals to 0. Okay, 0, A inverse into 0 is equals to 0. Now A inverse into A, B is equals to 0. What is A inverse into A? Which is nothing but 1 into B is equals to 0. B is equals to 0. I took A inverse but I got B equals to 0, right? Similarly, A comma B belongs to, means those are the elements of field. B not equals to 0 if we are taking, B inverse exists and therefore A is equals to 0. First we took A not equals to 0, A inverse exists, B is equals to 0, and here we took B not equals to 0, B inverse exists, then A is equals to 0. See, both the elements are fields. Either if we are taking one element is not equals to 0, we are getting another element as equals to 0, means either of A is equals to or B is equals to becoming 0, means any of the element if it is equals to 0, it has no zero divisors, means zero divisors definition it is not satisfying. So F has no zero divisors. If it has no zero divisors, just simply you can say that it is an integral domain. Okay, also they were asked that for converse, means for converse we have to give an example. Converse means what actually we have proved? Field is an integral domain. What is the converse part? Integral means every integral is an field. They were asking the question. No, it is not true. Okay, because the ring of integers, they are giving the example. The ring of integers is an integral domain but not a field, because only 1 and minus 1 have integers. Okay, 1 and minus 1 have integers. So our integral domain is not a field. Okay, but here we have the second theorem. But what is here? Show that every finite integral domain is a field. Okay, so in every integral domain is not a field, that is a converse part. But when it is a finite, okay, but when we are taking integral domain is a finite, then it is a field. Okay, we can give the example also for the here, right. So let R is a finite integral domain. What we are taking R as a finite integral domain. Finite means which we can countable. Okay, right. So A is not equals to 0 because it is an integral domain. Integral domain means it has no zero divisors. We have to satisfy. So A not equals to 0, which belongs to R. So what I am taking? A into R, which is equals to A into A1, A into A2 up to so on, A into AN, because we are multiplying the distinct elements with A. So the elements of AR are distinct because every element are different elements. AR are distinct. So now all those are distinct. I am taking, let AI is equals to AJ for I not equals to J, because those are distinct. So here I am sending these elements here, so it becomes AI minus AJ is equals to 0. Since A not equals to 0 and R is without divisor, R is without divisor, so what I can say? A minus AIJ is equals to 0, no? So which is nothing but AI is equals to AJ. AI is equals to AJ, which is a contradiction because these elements are distinct elements. Okay, these elements are distinct elements. We cannot say that AI is equals to AJ, which is a contradiction. Now what we are going to write down? Every element of R must be identical with exactly one element of R, one element of AR, means A1, A2 up to so on AN. So those two are equal. We need to write down A is equals to AKA for some K. Okay, if R is commutative, then A is equals to AK into A is equals to A into AK. So now we are taking one of the element that Z belongs to B, then Z into AK is nothing but what is Z? Here we are taking the Z elements are AJ into A into AK. So if I distribute to this law, if I apply the distributive law, AJ into A into AK, so AJ into AA is equals to Z. Okay, so which is nothing because the AK elements get cancelled and it becomes AJ into A is equals to Z. What we have proved, Z into AK is equals to A. Okay, here Z into AK is equals to Z we have proved. Z get cancelled, AK is equals to 1. If AK is equals to 1, R has a multiplicative identity. R has a multiplicative identity. What we are going to prove? We are proving it is an field, means it should exist multiplicative inverse. You have to keep that one in the mind. Okay, so from there I am writing R has multiplicative identity, means 1 belongs to R if it's there exists AI belongs to R such that 1 is equals to AI into A is equals to A into AI, therefore inverse exists. Okay, so whenever this property is satisfied, we can say that that element exists inverse. So every non-zero element in R has multiplicative inverse. If it is existing multiplicative inverse, therefore it is an field. Okay, so we have seen 3 theorems in this class. Please we will revise again. So what are those? No zero devices, if and only if cancellation laws hold in it. Okay, and every field is an integral domain, but converse is not true. Okay, right. And the next theorem is every finite integral domain is a field. We can give an example for an infinite integral domain. Okay, right. We will see in the next video the other theorems. Thank you.